back to the Nanoscope episode 3. I had to chop this one into 2 parts just to make it easier to listen to. Let's get back to our interviews with chemists as they continue to piece together atomic theory. And a quick reminder, when we left off, the atomic model was a clump of positively charged protons with a cloud of electrons orbiting around it. Niels Bohr, thank you for joining me. Now, what is it that chemists saw that made them question Ernest Rutherford's atomic model?
Yes, it was the spectrum lines that did it, I think. You see, when you have a tube and you fill it with pure gas and you bombard it with electricity, you send heat and energy through it, it glows bright colors. But when you look at it through a prism, it does not smear light. The energy being given off by it is these exact lines of color, these exact perfect lines, and that could not be explained.
So what then? Did chemists throw out Rutherford's model?
Yes, I feel like many did. You know, it's easy to throw out a model that was less than 10 years old. It's very hard to throw away, I don't know, 200 years of physics, but that's what I did. I decided to assume Rutherford's model was correct. I like to play tabletop games like ping pong and such, talk to my friends about what I thought, and I thought perhaps the orbits, the things the electrons spun around the nucleus in were exact according to which element it was, and that the electrons jumped between orbits, and that they gave off these exact chunks of energy and light that were exactly the same every time. They came to be called quanta, little quanta of energy, little packets, so you say, of energy that would come out, and if the jump was always the same, you would always get these perfect stripes of whatever energy would come out, and that's how I explained it. I just edited the model a bit.
So there was a new atomic model.
Yes, I suppose. Rutherford thought that the electrons orbited like the planets. I thought they orbited in these exact set-in-stone orbits that they jumped between. They did not move between them, and that threw physics on its head. I mean, what can I say? It's impossible for something to just be somewhere and then be somewhere else, but that's the only thing that could explain what was going on with the spectrum lines, seeing the light the gases give off through a prism. It was the only explanation.
So, can you then explain for me a little bit about how the spectrum lines worked? How were they given off?
Well, think of it like a ladder. Electrons want to be at the bottom of the ladder. They want to be at ground state, but when hit by a passing electron, by electricity flowing through, they jump up to a higher orbit, and then they jump back down. There's no traveling. They just disappear and reappear. And when they jump back down to the bottom of the ladder, they give off an exact quanta of energy, an exact amount of energy based on the distance they jumped. And for every atom, the distances of the orbits are slightly different. And that gives you different quanta of energy, and therefore different colored stripes.
So, what you're telling me, Mr. Bohr, is that everything I know about physics and movement doesn't work for electrons?
Yes, I suppose that's true.
Well, then, while I soak that in, I guess we'll just move on to our last question. Where was your motivation for studying science? Was it to find God, Mr. Bohr?
No, I can't really tell if I believe in God or not. Maybe that's why I studied science. Distraction. I didn't really find God necessary. Don't think a lot of chemists did. That was just the direction that society was going.
Well, thank you for joining me, Niels Bohr. And for our last interview, Erwin Schrödinger. Thank you for joining me.
Ah, yes, it's a pleasure to be here.
What contribution did you make to atomic theory?
Well,
I bet they think of me as a bit of a whack job, I guess. I added something strange, something that didn't make any sense. You see, when we tried to shoot electrons through two little slits, they would pop up all over the place on the other side. It didn't make any sense. So, electrons can't be particles if they can just pass right through these slits we made. They're like waves. Electrons are like wave particles. They're like probability. All an electron is the chance of whether or not you might find an electron there. But once you look, then the electron will either be there or it won't. But before you look, the electron is like a wave, not a particle. So my atomic model was a nucleus surrounded by waves of where the particle might be. So let me get this straight. Me looking at where an electron is makes it be there? I guess you could say that. The act of observation influences what's being observed. People don't act the same way when you're not there, but you can't look at what they might be doing because then you'd be there, and then they'd be acting as though you were there. Quantum physics works the same way. Quantum physics, you call it. Why that? Well, I guess it's from Niels Bohr. You see, he called the little packets of energy that teleporting electrons released, he called them quanta. And I guess the name just came from that. And Mr. Schrödinger, I have one more person on my list of interviews, but he refused because he was uncertain about it. His name was Werner Heisenberg. Can you tell me, did you work with him at all? Did he help you with this atomic model? Oh, Werner, uncertain as always. That was his principle, actually, the uncertainty principle. He worked a little bit more with Niels Bohr than myself, but still he came up with the idea that because light is required to find out where an electron is, and light knocks an electron out of position, that you can never know exactly where an electron is. If you're looking for its speed, you'll knock it out of place. If you're looking for its place, you'll have to stop it. So then you won't know its speed. I guess it was my and his atomic model, the cloud of probability. We were able to find out a lot about it, though, about where an electron might be, and it was very helpful for finding how molecules are formed and other things like that. But yes, Werner came up with the uncertainty principle, that the more you know about the speed of an electron, the less you know about its position, and vice versa. It was instrumental in the fundamentals of quantum theory. Thank you very much, Erwin Schrödinger. Well, I guess that's it, listeners. That's modern atomic theory right there. Of course, we've delved deeper into the probability of electrons and what quantum theory can do, and even teleportation itself. But that's the gist of it. But wait, hold on. What about neutrons? I know I've heard of those. Well, for them we have to look to James Chadwick, whose experiment comes all the way after all the rest of the things we've talked about. That's right. Electrons became clouds of probability before anybody was certain that there was something else in the nucleus besides protons. James Chadwick's experiment was very similar to his mentor's, Ernest Rutherford's, gold foil experiment, except he shot alpha particles through beryllium and noticed that an uncharged particle came out the other side. This led him to believe there were uncharged particles in the nucleus as well, and he called them neutrons. And so this leaves us with our final model of the atom, a group of protons and neutrons in the nucleus surrounded by electrons with weird and strange properties of maybe being there and maybe not being there. We also enter into the New Age science era, where science is a sort of combination of knowledge and religion, and that all science is the advancement of human evolution, and that eventually science will bring us to some higher state of existence, and that somehow science has lost the scientific method and become its own religion. New Age scientists also believe that the entire universe is all interconnected and that it's all part of one great consciousness and that God is everywhere and therefore inside us, and if we just think hard enough, then we can become God. Just goes to show you have to be careful not to take scientific discovery out of context. But that's for next time or for another podcast. Thank you for listening, and I hope this podcast has made you a little bit smarter. I'll see you next time. Quotidian. Compounds and other things of the such like. What does that even mean? Hello, I'm Werner Heisenberg. I can't do this voice.